This talk is about the power of recourse in online metric matching. It's joint work with Varun Gupta from University of Chicago and Ravishankar Krishnaswamy from Microsoft Research India. So we first start with introducing the problem. In the online metric matching problem, we have a metric space and we are also given k servers in advance. And k clients arrive one by one. And when a client arrives, we need to match it to one of the existing servers. And once a server is used, it cannot be used to match a different client. And so whenever this happens till all the k clients arrive, and the objective is to minimize the total length of the matching. That is the sum of all the edges used in our match. And like in any other online algorithms, our goal is to minimize the competitive ratio of the algorithm. By competitive ratio, we mean that the ratio of the cost of the algorithm and the optimal offline match. For example, in this instance, the optimal matching is denoted with the green edges. So for the algorithm, it doesn't know the optimal matching beforehand since it doesn't know the clients. But with respect to the optimal offline matching, we need to do well. That's the goal, and this has been studied quite a bit. One of the earliest works that introduced this problem, Kalyan Sundaram Press and Kullar Mitchell Vajrani, they proposed a permutation algorithm. We'll see the details about this algorithm later, and it achieves 2k minus 1 competitive ratio and arbitrary metrics. And they also proved that this is competitive ratio is tight. There also been some works on randomized algorithms for this problem. That is, with respect to oblivious adversary. There's log square k upper bound due to Bunzel and others, and there's also simple log k lower bound. The problem has also been studied in special metrics. In particular, on the line metric is a very interesting case. And in a series of works, the upper bound has been improved from order k in general metrics to log k by Sharath Raghvendra. There is also a lower bound of 9 plus epsilon. And interestingly, there is a lower bound of log k but for a very general family of algorithms called local symmetric algorithms. It turns out that all the algorithms that are in literature currently satisfy this local symmetric property. So really interesting gap between this constant and log k for the line metric. And our work is about adding recourse to the problem. So it is a relaxation of the original problem where we allow that certain clients can change their matching later. That is, this is the recurse model, and this you can formulate in different ways. For example, like if we say per client recurse, by that we mean that throughout the execution of the whole algorithm, a single client changes its matching at most t times. Or there's also amortized recurse where we say that at the end of the algorithm, the number of changes is at most t times k, and we say that the amortized recurse is t. And so the key question then is, can we get improved bounds for the online metric matching problem by allowing a small amount of recurse for the algorithm? In this work, we prove that it is indeed possible to do that. Particularly for the general metrics, we get a order log k competitive algorithm with the order log k per client recurse. So in contrast, in the general metrics case, there's omega k lower bound for without recurse for deterministic algorithms, and also for randomized algorithms, we only know log square k competitive algorithm. But with recurse, you can get log k competitive algorithm with log k per client recurse. And our main result is on the line metric where we actually get a of one competitive algorithm with log k recurse. And on the line metric without recurse, we, as mentioned earlier, we don't know any of one competitive algorithm, and that is an outstanding problem. So before going into the details, we first discuss the permutation algorithm. Permutation algorithm, it maintains offline optimal matches at every instant. So after I clients have arrived, let mi denote the optimal matching, and the algorithm is very simple. So first, when client first client arrives, it matches with the server output by the optimal matching. And after that point, whenever a new client arrives, we compute the new optimal matching between these clients and the total set of servers. And we pick the server that is in this matching and that is not used in the previous MI management. And turns out that this server is actually unique. There is a so at every these matchings M1, M2, and so on actually add a single server at any like keep adding single servers, and the algorithm just matches the new client with the server added by the algorithm. You can view this as some sort of an augmenting path. Whenever a new client arrives, the old matching is updated via new via augmenting path, and we just match the client and server that are at the ends of the augmenting path. For example, we now see an instance. So for first, when this client arrives, we compute the offline matching. Let's say it is matched to this server here. And so in the algorithm as well, we just match it there. And now a new client arrives here. We compute the optimal offline matching with these two servers, these two clients, sorry. And the matching is this. And note that this is the new server that is added. And so we just match the new client with this. Okay, so far so good. And now when a new client arrives here, the optimal matching changes and the new server added is this. So what we do in the permutation algorithm is we just match these two. We keep the old, recall that we cannot change the matching of the clients that are already matched. So we just keep the old matching and pair the new client with the new server that is now there. So we keep repeating the process. Now this client has arrived and we compute the full matching, and the server, the new server used is this. So we match here and so on. Finally, okay. Now we analyze the algorithm. The key claim is that the cost of every edge used by the algorithm is at most 2 This is because we can use this metric triangle inequality property to show that the edge cost is at most the cost of mi minus 1 plus the cost of mi. And it's not hard to see that the optimal matching of only like fewer clients is at most opt. So the cost of single edge is at most 2 times opt, and the first edge has cost at most opt. So the total cost of this algorithm is 2k minus 1 times opt. We can also study a batch version of this, which we need later, where in the batch version, instead of single client arriving, clients arrive in T batches. And at each batch, any number of clients could arrive. So the algorithm is again the same as before, where whenever a batch of clients arrive, we compute the optimal offline matching with the total clients arrived so far. And we match it to the augmenting paths, the ends of the augmenting paths with the by taking symmetric difference with the previous matching. And we can prove that by the same analysis that the commutative ratio then will be 2t minus 1. We now discuss our algorithm for the general metrics. So first we divide the input into square root k equal parts, b1, b2, and bp. Also note that here we assume that we know the value k, but this is by default since we are already know all these servers beforehand. So we do know k beforehand. So we divide the input into square root k equal parts. And first, when a client arrives, we run the permutation algorithm as before and match it with the server output by the permutation algorithm. However, after a whole batch has arrived, we apply the batch version of the permutation algorithm to the clients in the batch. For example, if we try to simulate the algorithm, first for all the clients in B1 from 1 to square root k, we run the permutation algorithm. After the whole square root k clients have read, we now compute the optimal offline matching with these clients, and we replace the existing matching with the offline optimal matching. And from this point onwards, this matching is fixed. This never changes. And now we move to the second block, okay, the square root k plus 1 onwards the clients. And whenever a client arrives, we run the permutation algorithm, find the server, and match it to it. We do this to all the clients in the second part. However, after the whole second part is done, the square root k clients have arrived, we now compute the optimal offline matching with B1 and B2, and then take the symmetric difference with the fixed matching to B1, and then use it as a matching for B2. Or in other words, we after the whole block B2 has arrived, we think that the first block is a single batch where we have run the permutation algorithm, and the whole sequence of clients in B2 is a different block, and we ran permutation for that. And so we update all the matchings in the clients. We do the same thing uh, till all the parts have arrived. We look at the analysis of the algorithm. First, we consider the cost analysis. So suppose that at any point, um, let's say some T blocks have arrived, and after the T blocks, some I clients have arrived. Note that by the property of permutation, the cost of those I clients is at most I 2 up times I, and the cost of first T blocks is also at most 2 T times 2 opt. This is because the property of the batch permutation algorithm. If we run the permutation with T blocks, it's 2T competitive. So combining the total cost, we know that at any point in the execution of the algorithm, the cost of the matching is at most like say 4 square root k, because 2 square root 4 square root k times opt, and because 2 square root k times opt is needed for the batches, and another 2 square root p is here for the batch that we are in. This type of this should be 4. Note that this is then is a 4 square root k competitive algorithm. Now we look at the recourse of the algorithm. So note that each client changes its matching only once. So first, when a client arrives, we run permutation and we find its matching. And after the block in which it is present finishes arriving, then we compute the batch for that batch permutation for that block, and we match it to a different server. So the each client is only has change only at most once. And now we this gives an algorithm with commutative ratio order square root k and recurse O of 1. We can actually this is an example, and we can modify it to get log k commutative ratio and also log k recurse. We now present our algorithm for the line metric. So before going into the algorithm, we discuss some properties of matchings on the line. First, we fix some notation that always we draw the arcs from clients to servers. And when a client is to the left of the server that it's matched to, we say the arc is forward as this blue arc. In the other case, we say it's backward. The key property of the line metric is that a matching is optimal if no two forward and backward arcs intersect. For example, here this red arc and the blue arc intersect inside this region. So this is not optimal, and here no two forward and backward arcs intersect in an open region. So this is optimal. The the reason this is true is because we can write the cost of the optimal matching as summation over all the atomic intervals. By atomic intervals, we mean the intervals between any two consecutive clients and servers. So, for example, here, you, um, and and furthermore, you could write the cost in terms of discrepancy at these intervals. So, for example, in this arc, there's to the left of this, the difference between number of clients and servers is 1. So in the optimal matching, this arc is used at most at exactly once, and that is the case if there are no crossing arcs. And similarly here, the discrepancy is 0. So in any optimal solution, this arc shouldn't be used, and the same is happening here, and so on. So we need to use this key property that there shouldn't be any intersecting forward and backward arcs. So how do you use this property to get an algorithm? So one idea is to come up with this cancellation type of algorithm. So by cancellation, we mean something similar to what we did here. So we just interchange the clients and servers of two arcs so that if they're intersecting before, they no longer intersect. Uh, if they are for one of them is forward and one of them is backward. So one idea is to do this cancellation whenever there are intersecting forward and backward arcs. So for example, okay, we run this instance. If a client arrives, we just run permutation first and find the server. And if there are no intersecting forward and backwards, we just keep it as it is. However, now after this client C2 has arrived, this backward arc and this forward arc are intersecting. So we cancel these two and obtain this. So we rematch these two clients and obtain this. And again, after a new client arrives, here there are multiple arcs that intersect with the new arc. So we just cancel them one by one to obtain the final solution, final matching like this. So this cancellation algorithm has this very nice problem that it always maintains an optimal matching because at any point no two forward and backward arcs are intersecting. However, the catch with this is the recourse could be very high. So even in the example that we have seen, the recourse is very high. So for example, if now there are all three backward arcs and the new client comes and the permutation matches, if the permutation algorithm matches to something like what, now everything shifts to blue arcs now. So if, the recourse could be as high as omega k in that case. So what this tells us is that we need to do some sort of specific cancellation. Like we cannot afford to cancel every time. Of course, this means that we will no longer have optimal solution, but it's okay for us. We don't need exact solution. We're only aiming for approximate solution. So we now get to our main idea, which is to cancel only one of the direction arcs in one of the directions. So we only cancel the backward arc. So if we run the permutation algorithm, and so suppose if we have something like this, we don't change the matching of client C2. We just keep it as it is and go forward. However, if the situation is like this and then C3 arrows, we cancel these two. So we cancel the backward arcs. So now we go into the details of the cancellation. So I just explained that we need to cancel multiple arcs recursively or something like that. But there are some tricky parts involved in that. So how do we cancel if there are multiple arcs? So for example, here there are many forward arcs and a backward arc has arrived. How do you cancel? Which forward arc do you choose? So that is a you can come up with different algorithms based on different notions of this choosing which forward arc. But one very important property is that this cancellation is equivalent to replacing the existing matching with the optimal matching between certain client, like the clients that have forward arcs that intersect with this backward arc, and the servers those clients use. So, and again, there could be multiple optimal matchings, and all of them lead to different solutions. But one nice property is that all these solutions actually have the same competitive ratio. It's not too difficult to prove because we again use the previously mentioned property of the cost of matching on a line, where we write a cost in terms of the discrepancy of intervals. And so, since all of these have equal cost, we give two different algorithms, one called recursive cancel and another called minimum cancel. And both these algorithms have the same cost at any instant. However, recursive cancel is much easier to analyze the cost. So we present it first. So in the recursive cancel algorithm, when a forward arc arrives by as an output to permutation, we just add as it is. And when a backward arc arrives, we look at all the clients that have forward arcs that lie inside this backward arc. Okay, for example, here C1, C2, C3, C4, and we find the client with the farthest server among them. So for example, here it's C4. So we just cancel C4S4 and C5S5. And so we obtain this new semi-instance. Like it's not a new client or anything, but we just made some changes. And now in the backward arc that results from this change, we again do the same operation. We recursively pick the client with the farthest server among the clients which have forward arcs inside this region, inside this arc. So that's C3, and we again cancel C3S3 with C4S5. So we obtain this, and we keep doing this process. Ultimately, when the backward arc that we added doesn't intersect with any forward arcs, we stop the process. So this is the recursive cancellation algorithm. As we can actually see in this very instance, this could have very high recourse. So note that this type of a structure where C1 is mapped to S1 and so on is appears again here. The same structure appears here. So if you have a lot of them here, something like K over 2, this algorithm will have amortized recourse of omega K. So in order to counter that, we propose a different algorithm called minimum cancel, which cancels the minimum number of, it changes minimum number of arcs among these, but still maintains the cancellation property that at the end of this thing, there are no intersecting forward and backward arcs. So we could do this process iteratively, but the goal is to do this greedily at for every backward arc. We add forward arcs as it is, and when a backward arc comes, you look at all these clients and servers. You find a new optimal matching between these that have no intersecting forward and backward, but change the minimum number of arcs. So this is the minimum answer. And no, as mentioned earlier, both the algorithms have the same commutative ratio. However, our final algorithm is minimum cancel, and we analyze the recurse of it. Uh, to analyze the cost of recursive cancel, as mentioned earlier, we look at the discrepancy and between the clients and servers, and we also this is the point where we use properties of permutation algorithm, some optimal properties, and um, that there are a lot of details involved. I'm just skipping them for now. For the analysis of recurse of minimum cancel, we use this potential function of log of the number of server inside an arc, summation of it. And can prove that this potential function goes down by 1 for every change that you make. As the total function is at most k log k, this gives us that the recurse is at most log k. Also note that it's still open whether our algorithm actually gives O1 recurse. It is still possible that the same algorithm, maybe some modifications to make it easier to analyze, could give O1 recurse. As mentioned, right now it's 3 competitive, but log k recurse, only upper bound. We don't know lower bound. And finally, we conclude by saying that we propose a new recurse model for the online metric matching, that is of log k competitive on general metrics, and with of log k recurse, and there's also 3 competitive on the line metric with amortized log k recurse.